Okay, section 2.2, understanding polynomial functions and their graphs. We talked about some of this in class. We're just going to keep going, but first I want to run through the things we already talked about. Let n be a whole number, and a sub n minus 1, a sub n minus 2, and so on. Let those be real numbers, where a sub n is not 0. Then the function defined by f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 to the times x to the n minus 2, and so on, all the way down to a sub 0, which would be a constant. That is called a polynomial function. And to be a polynomial function, the coefficients have to be real numbers. So all those a's with the subscripts, those all have to be real numbers. The coefficients have to be real numbers, and the exponents on x must be whole numbers. So coefficients have to be real. The exponents have to be whole numbers. You can tell that that polynomial function on the left, that is a polynomial function. It has all the things that we just said. The coefficients are real numbers. The exponents are whole numbers. It's all good. The one on the right is not a polynomial function because square root of x, that's x to the 1/2. So the exponent on x is not a whole number. 3 over x means 3 times x to the negative 1, which means the exponent is not a whole number. It's a negative integer. And 3 plus 2i is a complex number, and the coefficients have to be real. So this is the difference between a polynomial function and something that is not a polynomial function. Sometimes polynomial functions of certain degrees have names, like a third-degree polynomial function is called a cubic polynomial function. A fourth-degree polynomial function could be called a quartic polynomial function, but most of the time we just talk about the degree, third degree, 12th degree, 9th degree. We don't really give them special names, but some of them have that. Like a quadratic function is a second-degree function, and a linear function is a first-degree function. The domain of any polynomial function is all real numbers, because polynomial functions don't have variables in the denominator, so you don't ever need to worry about a denominator being 0. And the polynomial functions don't have square roots. They don't have the square root of a variable either, so you don't have to worry about getting a negative number under the square root. So polynomial functions will always have a domain of all real numbers. Anything, you can put any number in there, any real number. The graph of a polynomial function will be a smooth and continuous curve like the one on the left. It's not going to have any sharp points like the absolute value function. It's not going to have a break in the graph like the inverse function, or holes in the graph like the one on the far right, which is probably a piecewise function. A polynomial function will be smooth and continuous. A power function looks like f of x equals x to the n. That's all there is to that function, just x to some power. This kind of function is called a power function, and they all look, the even ones look like a parabola, the odd ones look like a cubic, and that's just all you need to know about a power function. But you do need to know that the end behavior of a function is the general direction that the function follows as x approaches infinity or negative infinity. Right? Remember that little arrow means x approaches infinity. So the leading term of a polynomial function dictates the end behavior of the function, because as x gets very big toward infinity or negative infinity, the absolute value of the leading term will become larger than the absolute value of all the other terms combined. Okay, so at first you might think, wait a minute, what are you saying? How can it be that the leading term of any polynomial function, the first term, how can that just outweigh all the other terms combined? And I'll just show you an example. All right, suppose you have this polynomial function, f of x equals 4x to the 5th minus 3x to the 4th plus 2x cubed minus x squared plus x minus 5. And suppose you put in there just a basically moderately large number, not a humongous number, but a large number like 1,000. Right, that's 10 cubed. If I put that into the function, what am I going to get? All right, well, 4 times 10 cubed to the 5th is 4 times 10 to the 15th. And then you've got minus 3, 10 cubed to the 4th is 10 to the 12th. And then 2 times 10 to the 3rd is 2 times 10 to the 9th. And then minus 1,000 squared is 1 with 6 zeros. And then plus 1,000 minus 5. If you punch that into your calculator, you are going to get this. Okay, that is almost exactly the same thing as the leading term. All the other terms don't even matter anymore. I mean, it's just like they're not even there, because that leading term dominates as you get bigger and bigger values of x. It dominates so much that the other terms don't even affect what the value of the function is anymore. And that's why we can just look at the leading term when we are trying to figure out what a function does on its way to infinity or negative infinity on the x-axis. So if you have a function f of x, polynomial function, as x approaches infinity or as x approaches negative infinity, f eventually becomes forever increasing or forever decreasing and will follow the general behavior of the leading term, which looks like the power function a sub n x to the n. So if you have an even power on your leading term, 2, 4, 6, whatever, then what that means is no matter what you put in for x into that leading term, that x to whatever that power is, that even power, will always be positive. And so that means that the graph will, just get bigger and bigger. However, if the leading coefficient, a sub n, the number that's being multiplied by that even power of x, is positive, yeah, then both ends will keep going up and up and up. So on the left there, if the leading coefficient, a sub n, is positive, and you have an x to the n, which has a even power, then as x gets bigger and bigger positively, as x goes to infinity, that function is also going to go to infinity. It's going to shoot up. As x goes to negative infinity, you're still going to get positive values because a negative number raised to an even power is positive, and you multiply by that positive coefficient, and it's still positive. So even function, leading coefficient positive, that means that the graph shoots up on both sides. However, if the leading coefficient is negative, then your graph is going to shoot down on both sides because x raised to the even power, that's always going to be positive, but if you multiply it by a negative coefficient, it's going to be always negative. So if the leading coefficient is negative and the power on x is even, you're going to have a function that approaches negative infinity as x approaches infinity, or negative infinity, either one. It's going to shoot down on both sides. So that's if you have an even power. If you have an odd power, you're going to have up on one side, down on the other. And it just depends on your leading coefficient what is going to happen. All right, if you have an odd power on x, that means if you put in a positive number for x, you're going to get a positive number. If you put in a negative number for x, you're raising it to an odd power, it'll be negative. So if the leading coefficient is positive, then if you put a positive number in for x, so on the right side of the y-axis where all the x's are positive, so as x approaches infinity, you're multiplying a positive number by a positive number, you're going to shoot up towards infinity. But if you put in a negative number into an odd function, you get a negative number. So on the left side of the y-axis, that function will have a negative value because you're raising a negative number to an odd power, and the coefficient is positive, so it's not going to change that. It's just going to keep going negative. So if your leading coefficient is positive and the power on x is odd, the function will approach negative infinity as x approaches negative infinity, and the function will approach positive infinity as x approaches positive infinity. However, if you have an odd function and the leading coefficient is negative, then it's going to be the opposite way around. Because if you have an odd function and you put a positive number, a positive x value into that function, so on the right side of the y-axis where you're putting in positive values for x, that function will have a positive value, but it's being multiplied by a negative coefficient, so it becomes negative. So for this situation on the right, as x approaches infinity, the function approaches negative infinity. On the left side of the y-axis, where all the x's are negative, when you put a negative number into an odd function, you get a negative number. However, you're now multiplying it by a negative coefficient, and so it flips it and it shoots up to infinity. So if a sub n is negative, the function will approach positive infinity as x approaches negative infinity. And that is just a huge mouthful of stuff to say, and it's really confusing. You really have to just sit there and stare at it for a while and think about it to get a handle on it, but it does totally make sense. So use the leading term to determine the end behavior of the function. All right, so we have beaten this thing to death. We ought to know how to do this. So let's look at the leading coefficient. It is negative 4x to the fifth. The exponent is odd. The coefficient is negative. And that means that as x approaches infinity, what is happening to f of x? Well, let's think about it. As we're going further and further that way, we're getting positive values, putting them in for x. That x to the fifth is positive. However, we're multiplying it by -4 every time, so that makes it negative. So as x gets big, this function is going to shoot down. All right, so as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, so going this way, what's happening? X is negative. If you put a negative number into x to the fifth power, you're going to get a negative number. However, you're going to multiply it by -4, which is going to make it positive. So on the left side of the y-axis, where the negative x's are, this function is going to be going up. So as x approaches negative infinity, f of x approaches infinity, positive infinity. So this function goes up on the left and down on the right. To get your leading term, first of all, if you cube this binomial right here, you're going to have an x cubed going on there. And when you multiply that by x to the first, you're going to have x to the fourth. And then you multiply that by an x squared over here, you're going to have x to the sixth. So leading term, this is going to have it's going to have a power of 6. All right, if you multiply it all out, you will get 6, but you can see that that's what's going to happen, even without multiplying it all out. So x to the sixth, and then you can see that the coefficient on x is going to be positive. So positive coefficient, even exponent. That means that as x approaches infinity, you've got a positive value going into an even function. That's positive. You've got a positive coefficient. That's positive. So as x approaches infinity, f of x also approaches infinity. So it's going up on this side. As x approaches negative infinity, okay, you're putting negative values into the function. You're raising it to the 6th power. That becomes positive again. You're multiplying it by a positive number, still positive. So it also goes up on that side. So as x approaches negative infinity, f of x still approaches infinity. Okay? So that's how you figure out the end behavior of a function. You just look at the leading term and figure it out that way by the power on x and by the coefficient, the sign on the coefficient. The zeros of a polynomial are the values of x that if you put them into that polynomial, you will get 0. They are also the solutions of the equation f of x equals 0. They are also the x-intercepts of the graph. So sometimes those 3 words can kind of be used interchangeably, but they do have slightly different meanings. So the zeros of the function, the solutions of the function, equation f of x equals 0, and the x-intercepts of the graph. Those are all the same things, the same values of x. So if you want to find the zeros of this function, all you have to do is solve the equation x cubed plus x squared minus 9x minus 9 is equal to 0. So you would have x cubed plus x squared minus 9x minus 9 equals 0, and you would have to factor it. And we did this in class. You'd have to factor it by grouping. You would factor this out this way, and this is not something that always happens, but when you have something like this where you have a cubic equation and there's no common factor to factor out, you have to try something, and this is one of the things you can try, which is to factor by grouping. And when you do this, you can factor out the x plus 1, and you're left with x squared minus 9. And so since you know the zero product property, you know that either x plus 1 is 0, which means that x is -1, or x squared minus 9 is 0, which means that x squared is 9, or x is equal to plus or minus the square root of 9, which is 3. So there are 3 zeros of this function, and that's as it should be because the highest power on x is 3. You should expect 3 zeros. they won't always be real zeros. This one has 3 real zeros. So those would be called the zeros of the function, and those would be the places where that graph crosses the x-axis. All right, if you wanted to find the zeros of this function, you would again set it equal to 0. So you'd have negative x cubed plus 8x squared minus 16x equals 0. And then you can see that you have a common factor of x. So you could factor out negative x, and then you'd have x squared minus 8x plus 16 equals 0. And then you can see that x squared minus 8x plus 16 is just going to be x minus 4 quantity squared. And so you can see that the two solutions to that equation, since two things are being multiplied together to give you 0, one of them has to be 0. So negative x is 0, which just means that x is 0. And x minus 4 is 0, which means that x is 4. So there are two zeros of that function. This one would be called a zero of multiplicity 2. So there really are 3 real zeros. It just happens that 2 of them are the same number. Okay, so finding the zeros of a function, as I was saying, is very important because it tells you where the function crosses the x-axis. And sometimes that's, you can't find very many points on the function to call home. Their functions become more and more complicated. You need to have some places where what is this function doing? When does it become positive? When does it become negative? And knowing when that happens is knowing when it crosses the x-axis. If a function is in negative territory, if its value is negative, it's below the x-axis. If its value is positive, it's above the x-axis. So when it crosses the x-axis, we know that something happened. It changed signs. And so knowing where the function is going to cross or touch the x-axis is a key important thing to know about so that you can graph it. All right, so we say that if a polynomial function has a factor x minus c that appears exactly k times, then c is a zero of multiplicity k. And that sounds complicated, as all mathematical definitions do, but it makes a lot more sense if you look at this. So for example, for the function g of x, it's all factored out here, x squared times x minus 2 cubed times x plus 4 to the 7th. You can see the zeros of this function, of course, because if it's factored and you set it equal to 0, you know that the three things multiplied together give you 0. So one of them has to be 0. So either x squared is 0, in which case x is 0. So that's a 0. X minus 2 could be 0, which means x would be 2. Or x plus 4 is 0, which means x is negative 4. So these are the zeros of this function g of x. But some of these zeros kind of count more than once. We would say that 0, okay, that 0 has a multiplicity of 2 because there are two factors that represent that 0. And then when x is 2, so we call that 2 is a 0 of multiplicity 3. And then for negative 4, that there are 7 factors of x plus 4. So that means that negative 4 is a 0 of multiplicity 7. So if c is a real 0 of a polynomial function f, then c0 is the x-intercept of the graph of f. And if c is a 0 of odd multiplicity, then the graph actually crosses the x-axis at that point. The point c0 is called a cross point. Okay, so if you take a look at this function on the right, f of x equals negative x times x minus 4 squared, so the zeros of this function are going to be 0. So that's a place where it crosses the x-axis. And also x equals 4 is a 0 of multiplicity 2. And 0 is a 0 of multiplicity 1. And what we're saying here is that if c is a 0, which in this case 0 is a 0, that's hard to say, of odd multiplicity. I mean, it's only of multiplicity 1, which means that's odd. 1 is odd. That will tell you that the graph crosses the x-axis. It actually crosses it. So it's down here, it crosses the axis, right? That you will know if the 0 has a multiplicity that is odd. If c has a multiplicity of an even multiplicity, like the 4, that has an even multiplicity because remember, there were two factors of x minus 4. That would be 4 is a 0 of even multiplicity. Then the function will only touch the x-axis. It will come up, it will touch it, and then it will go back down. Or it will come down and touch it and go back up. That's called a touch point. So all these clues, these ways of analyzing polynomial functions, what you're doing is you're collecting clues so that you can sketch the graph. Back in the day when you just graphed lines, you knew exactly where to put it, you knew exactly where all the points were, didn't take much to figure it out, and you knew that your drawing was perfect. Not so with polynomial functions. Sometimes even after you find all the things you can find out, you still won't be exactly sure if the graph looks exactly the way it should. But this is one more thing to know. If you factor it out, if you find the zeros and their multiplicities, you will have found the x-intercepts. And if you know the multiplicities of those zeros, if they have an odd multiplicity, the function will actually cross the x-axis at that place. If they have an even multiplicity, it will just touch the x-axis at that point. All right, so we're going to determine the zeros and their multiplicities for the given functions. All right, you can see that there are 5 factors here. So either x minus 4 is 0, or 2x plus 5 is 0. So this means that x equals 4, and that is a 0 of multiplicity 2. So I'm just going to go ahead and write that. And then 2x plus 5 equals 0, which means that 2x is negative 5, which means that x equals negative 5 halves. So that's another 0, but this one has a multiplicity of 3. All right, so for n of x, again, we're trying to find the zeros of the function. So we set it equal to 0 and we factor it. So if we factor out x squared, we're going to have x squared minus 2 left here. So x squared could be 0, which means that x would be 0. Or x squared minus 2 could be 0, which means that x is going to be plus or minus the square root of 2. So there are 3 zeros. 0 is a 0 of multiplicity 2. Square root of 2 is a 0 of multiplicity 1. And negative square root of 2 has a multiplicity of 1.